Let's review our partial differential equation. Actually, so far we just learned two types of equation. First, let's see the unsteady heat equation. So my partial differential equation is partial u of partial t alpha partial square u partial x squared. Okay, so every time when you have an equation, you need the boundary conditions and also initial conditions to solve that equation. So first, when we learned heat equation, actually we have 4 different types of boundary conditions and initial conditions. So first, let's see for the boundary conditions. The first one is on the boundary, it's O0. And their initial condition at t equals 0, I have a function. That's the first one. Second one. The second, if I take the derivative, then it is 0 at the boundary. And we also call that this condition is Newman boundary condition. So Newman boundary condition. Then the third one, u of at 0 at the boundary, that's 0. And the other one, if I take the derivative, it's a function. And this is a convective boundary condition. Last one. Oh, and also for those two, the initial conditions are the same. Initial conditions are the same. And the last one, I only have one side of boundary condition, that's 0. And then initial condition still equals f of x. And this one is the semi-finite bar. Semi-infinite bar. And what is the solution for this differential equation? We only learned one. That is called separation of variables. So the solution for this solution I have x and I have a t. And if you bring the solution back to your partial differential equation, you get the derivative of x on one side and the temperature on the other side. They should be equal. They are equal unless they are constant. It's also called separable constant. And conventionally, we assign this constant as minus lambda squared. So no matter which boundaries we have, they are the same. Okay, for the solution, separable, and then we can get two ordinary differential equations. The first one and the second one for temperature. For the x, that's the linear combination of your cosine function and sine function. And for the temperature will be a constant times, or the coefficient times exponential. So this is our solution. Okay. Then once we have a solution, how do I determine those coefficients? Using the boundary conditions and initial condition. We always deal with the boundary condition first to check A1 and A2. Okay, so for the boundary condition, in the first type, we will get which one will be 0, A1 or A2? Which one? When we plug in the boundary condition, x equals 0 equals 0, A2 equals 0, or A1 equals 0? A1. So here, for the first type, A1 is 0. So your x is A2 sine lambda x. That means your xn, well, you put another boundary condition, you get an sine n pi over L. X. And then your T temperature at N, that's Bn exponential minus n squared pi squared over L squared alpha T. And overall, it's just plugging and you'll get an for x, an sine m pi over L x, and your T, the temperature, Bn e to the minus n squared pi squared over L squared alpha t. You can combine the coefficients an and bn, so you get cn and sine m pi over L x times exponential minus n squared pi squared over L squared alpha t. And then your n is from 1 to infinity. So finally, your solution is a linear combination of your un. So Cn sine m pi over L x times exponential and then we can use the initial condition to solve the coefficient Cn. That is for the first one. Okay, the boundary conditions are all zeros. Now how about the second one? Newman boundary conditions. In this case, you also take the derivative. Well, and bring the boundary conditions to here. So which one will be 0? A1 will be 0 or A2, or none of them are 0. You take the derivative and then put 0 here. So there'll be A1 sine and A2 cosine, and put 0 here, and that should be 0. So for the second type, your A2 should be 0. And then your x is A1 cosine lambda x. So your xn is having another boundary condition, then you get xn will be an cosine, and you can find the lambda m pi over L times x, and your temperature Bn exponential minus n squared pi squared over L squared lambda t, alpha t. And you do the similar thing. Now sine becomes cosine. How about the third one, the convective boundary condition? So it's still x0 is 0, same thing. So apparently here A1 should be 0. Okay. So A1 should be 0, and your x is A2 sine lambda x. But from the other boundary condition, you get A2 lambda cosine lambda L equal to minus h A2 sine lambda L. So you get tangent lambda L equals minus lambda over h. And we call lambda L becomes z. So lambda n equals z over L, zn over L. Then your temperature is coefficient Bn exponential minus Zn squared over L squared alpha t. Okay, last one. Again, that x equals 0, that's 0. So which coefficients will be 0? They're the same, right? So a1 should be 0. Now your x is a2 sine lambda x. And your temperature, T lambda, is B lambda times e to the minus lambda square alpha t. Okay, and then you can use the drills or some class examples to refine your solution. Okay, follow those steps. Any questions about the heat equation? Next, let's talk about the wave equation. So here we have a wave equation. Partial square y over partial t squared equals a squared partial square y over partial x squared. First, let's see. In this case, we have three different boundary conditions and initial conditions. For boundary conditions, at the boundary, that's 0. And the initial condition at 0, that's 0. And for the speed, initial speed is also 0. That's a 0 initial velocity. And the other one is non-zero initial velocity. So the boundaries are the same. Y over 0, t is 0. And at the boundary, it is still 0. But for the initial conditions, here for the initial velocity, it is not 0. It's a function. So this is non-zero. Initial velocity. And finally, we have an infinite string. So we don't have boundary conditions. Infinite string. So no boundary condition. And for your initial conditions, at 0, I have a function, and when I take the derivative, it's 0. Or it could be the combination. Remember that if it is not 0, then we will combine this solution plus this solution together. So for the overall solution, no matter which types your solution is, Also using the separation of variables, we get x times the time t. Bring this back to the differential equation. We have x double prime divided by x equal to t double prime a squared t. And again, that this is the position, this is the time. They are equal until this is a constant. Otherwise, position is position, time is time. They cannot be equal. So for the constants, conventionally we have a minus for your constant. So minus lambda squared. Then you have x double prime plus lambda squared x equals 0, and t double prime plus a squared lambda squared t equals 0. Right, so now for the first one, with initial conditions, we get your Tn is coefficient times cosine m pi a over L t. For non-zero initial velocity, we have Qn sine n pi a over L t.